One of the facts about enrichment of uranium for nuclear power reactors by gaseous diffusion is that the product is only about 15% of the UF6 process gas that is fed into the plant. The other 85% of the feed is removed as depleted UF6 and stored in cylinders at the plants. At present, there are about 40,000 of these cylinders at K25, Paducah, and Portsmouth. They are in specially prepared storage lots, and to save space, they are closely spaced and stacked too high, making it difficult to see all their surfaces. These are some of the cylinders stored at Portsmouth. The cylinders are made of steel, 4 feet in diameter and 12 feet long, and each one contains 14 tons of UF6. Nobody knows exactly what UF6 looks like inside a cylinder because we do know that it is a solid and a gas because the temperature of the material is below the 147 degree Fahrenheit freezing point of UF6, so there is no liquid. The solid mass of UF6 occupies about 62% of the cylinder volume, while the rest is filled with gas. In a properly filled cylinder, there is only UF6, no air or anything else. Therefore, we know the gas pressure above the solid is about half of the atmospheric pressure of 29 inches that the TV weather girl tells you about every evening. In other words, there is a vacuum in the cylinder. This picture of UF6 sealed in a glass tube shows the solid, almost white crystals and the colorless gas filling the rest of the tube. Probably this is similar to what UF6 looks like in a cylinder. A very detailed inspection of the cylinders at Portsmouth was made, and quite unexpectedly, 2 of the 8,000 cylinders stored there were found to have holes in their sides. These holes were initiated during stacking by a lifting lug on one cylinder hitting another cylinder with such force that the cylinder wall developed a small crack on a welded joint. In both cases, the location of the damage was in the solid region of the cylinder. Moisture from the air, as well as from dew, rain, snow, and fog, slowly seeped through the crack and reacted with the UF6 to form hydrofluoric acid and solid uranium reaction products. The acid dissolved in additional water and reacted with the steel at the hole and slowly enlarged it during the years of storage. This is the cylinder with a small hole. It was placed in the yard about 4 years ago. The opening is about 3 inches long by 1.5 inches wide and is located near the lifting lug on the valve end of the cylinder. And this is the big hole cylinder. It was damaged when it was placed in the yard, and the breach has been slowly enlarging during its 13 years of storage. It is now about 15 inches long and 8 inches wide. The green solid is hydrated UF4, and the light-colored solids are hydrates of iron fluoride. These solid reaction products adhere to one another in a dense mass that effectively plugs the holes, preventing the release of significant quantities of uranium. This is demonstrated by the facts that the internal gas pressure of the small hole cylinder is a vacuum, only slightly less than an undamaged cylinder would be, and the total weight of the cylinder is the same as when it was placed in storage. The big hole cylinder has an internal pressure of about 1.5 atmospheres. A sample of this gas showed it to be UF6 mixed with some of the HF that had been produced by the corrosion reactions. The present weight of the cylinder, plus the weight of the solid reaction products that had fallen to the ground, accounts for all but 7 pounds of the UF6. To continue the investigation, both cylinders were patched with contoured aluminum plates so that the UF6 could be removed safely by evacuation without heating. Pipe couplings and plugs were installed on the big hole patch to allow insertion of a hollow tube into the plug to obtain a core sample of the solid. The gauge is to permit testing the patch. Here the men are removing the pipe plug prior to inserting the tube to pierce into the plug and collect the samples. This is the first core removed. You can see the same green and yellowish tan colored materials that was seen in the holes before they were covered with the patches. there is no UF6. In attempting to get a second sample, the transparent sample tube broke because the plugging material was so hard. A sharpened piece of pipe and a 3-pound hammer were then used to get additional samples. It was possible to get 10.5 inches into the solid mass before the pipe encountered something so hard that it could not be driven in anymore. The sample obtained when the pipe was removed was similar to the first one, and again, there was no UF6 in the core. While the big hole cylinder was being retrieved and sampled, the 14 tons of UF6 in the small hole cylinder was removed as a gas by evacuation without heating and preparation made for internal inspection. This is the kind of valve used on these cylinders. It is the only opening into the cylinder, so the packing nut and valve stem were removed to permit the insertion of a fiber optics TV camera to view the inside of the cylinder and the interior side of the plug. The camera is 1/4 inch in diameter and has its own light source. It is mounted inside a piece of copper tubing long enough to allow the cameraman to get it to the vicinity of the plug, which is about 4 feet from the valve opening. Unfortunately, there is a flaw in the lens which shows in the lower right of all the pictures. As the camera enters the cylinder, you saw the inside of the valve, and this gives you an idea of the detail that the camera can pick up. This is the inner surface of the cylinder wall. The tan-colored substance is iron fluoride that was formed when UF6 was first introduced into the cylinder as it was being filled 4 years ago. This coating provides a protective film on the steel surface that prevents further reaction between the UF6 and the steel. The bare spots are where the coating has been dislodged during the handling of the cylinder after the UF6 was removed. Now we see the plug as the camera moves over its surface. The orange-colored material is a dry uranium oxyfluoride, which was formed at the interface between the solid UF6 and the plug during the plug formation. This color will turn yellow when the material picks up additional water and becomes hydrated. Because of the limited field of view of the camera and the difficulty of maneuvering it, you cannot tell the full size of the plug or the conditions at the juncture of the plug and the cylinder wall. The next step in the investigation will be to cut out the damaged section of the cylinder wall to be able to see the plug in full size and get pictures and samples of it, and to perform a detailed metallurgical examination of the corroded steel. When this has been completed and the data evaluated, then we will know the whole story.